Today we're taking a look at lesson 6.2. Again, we're going to be working with two variable linear systems. So if you guys would open up your textbooks to 6.2, I think you'll find that one beginning on page 434. We'll take a look at another method today. All right, so the method that we're going to be looking at today is called the elimination method. In the past, you may have referred to this method as the combination method, but what we're going to be doing is eliminating one of the two variables that are in our system by creating opposites. Once we have opposites with either our x terms or our y terms, we're going to combine. We'll add those two equations together, thus eliminating one of our variables. So those of you who are kind of step people, I wrote up a general 5-step process for this, so you are welcome to copy this down and follow that. Many of you might remember this method from the past, so you might not find that it's necessary. Okay, so let's put it into play. If we had this system, this is checkpoint number 1 found on page 434. Notice in this system, we already have those opposites. We have a positive y in our first equation, and we have a negative y in our second equation. So this one is ready for us to combine. Those y's are going to eliminate each other. So combining the top one with the bottom one, our x's combine to make 4x. The y's again are gone, they are eliminated. 4 and negative 1 combine to make 3. Solve for x. Divide off the 4. X is equal to 3/4. I have now one numerical value for one of my variables. I can plug that into either of my two equations from my original system and find y. I'm just going to plug it into the top. So 2 times 3/4 plus y is equal to 4. Multiplying 2 times 3/4, I'm going to do a little canceling with my 2 and my 4. So I have 3/2 plus y equals 4. Subtract the 3/2 away. So y is equal to, now 4, I'm just going to rewrite that so you guys can see what I'm doing here. 4 is the same thing as 8 over 2. So now with my denominators matching, I can do the 8/2 minus 3/2, and I get a y value of 5/2. Solution to the system then is the point 3/4, 5/2. Let's do another one. Checkpoint number 2. This one's not quite as ready to go for us. And you can eliminate either the x value or the y value. Personally, I'm going with the y's on this one, only because one of them is already positive and the other one is negative. And I think that's a fewer steps to have to do. I only have to change one of my lines. So I need a negative 3y, which would require a multiplication of 3 through that second equation. So I'm not going to touch my top one at all. I'm just going to rewrite it off to the side here. And then I'm going to multiply that 3 through my bottom one. Okay. Combine. My y's are going to eliminate. I end up with 17x is equal to 68. Divide off your 17. And x ends up equaling 4. Now you can take that numerical value for x and plug it into either of your two original equations. I'm going to put it in the top one. And solve for y. Subtract 8 from both sides. And divide away your 3 coefficient. Solution. The pen got a little crazy there. X value was 4 and the y value 3. There's my ordered pair that solves the system. Checkpoint number 4 takes us into a system that involves decimals. There are two ways that you can go about solving this. I can go ahead and make opposites like I did with the other ones. You don't have to run from decimals necessarily, but you do have another option. Looking at my equations in this system, notice that all of them have 2 decimal places in them. all I'd have to do to that top line to eliminate any and all decimals is to multiply everything by 100. Okay, so I could do the same to the bottom one as well. Notice that that one had 2 decimals in all of its terms. I'm going to multiply that one by 100 also, and that way I'm going to clear every single decimal that's in my problem. So let's take a look at what it looks like after we do that. Multiplying through the top by 100. 0.03 times 100 is 3. So I get 3x, and then 4y, and 75. I think that looks much better. Second line, let's do the same thing. That one turns into 2x plus 6y equals 90. And now we can apply that process of elimination. On this one, I think I'm going to go with my x values. They are currently both positive right now, so I'm going to have to turn one of them into a negative, but that's okay. The top one, I think I'm just going to run a times 2 through that one, and I'm going to run a negative 3 multiplied through the second one. I'm going to get a 6x and a negative 6x then that will eliminate. All right, so let's look at what our new top equation is going to look like. Multiplying everything by 2. 2 times 3x is 6x. 2 times 4y is a positive 8y. And 2 times 75 is 150. Second line, multiplying through with a negative 3. Negative 3 times 2x is negative 6x. Negative 3 times 6y is a negative 18y. And negative 3 times 90 is a negative 270. We can combine. So the x's will eliminate each other. A positive 8y and negative 18y make negative 10y. And 150 and a negative 270 give me a negative 120. Divide by negative 10. So I find a y value of 12 using the system of elimination. Now I can take that 12, plug it into either of these two equations over here and find my x value. I'm going to go ahead and stick with the top. It really doesn't matter. So 3x plus 48 equals 75. Subtract 48. 3x ends up equaling 27. And I can divide by 3 on both sides then, and I finish with an x value of 9. So the coordinate, or the ordered pair solution here, is 912. All right, so let's back up and talk about the graphing method a little bit more. We worked on this with section 1. We know that when two lines intersect, they have a common point. What if they don't? All right, so we have a couple more situations to consider. Situation number 1 on this slide says the lines might be parallel. You guys know the definition of parallel lines. They are lines that go on forever and never cross or touch. Without a point of intersection, there aren't going to be any solutions for those two equations. All right, so watch for systems that have parallel slopes in the equations for it. If they're parallel, they won't cross. Another case that might show up for you is if the lines coincide. What that means is that they end up being the same line. Okay, so you graph one and then you end up graphing the other, and they land on top of each other. Coinciding lines have an infinite number of solutions. They have an infinite amount of intersection points because they overlap. So that's our second case that could show up. 3 on the slide here is kind of what we've been dealing with. Lines that intersect in exactly one spot are going to have exactly one solution. So let's take a look at this system. It's checkpoint number 5 on page 438. If we're going to solve this with graphing, the first thing we're going to want to do to these equations are get them into, or I prefer to get them into y equals mx plus b form. So if I'm going to do that to my top equation, I want the negative 2x to go to the right-hand side. So now I will have 3y is equal to a positive 2x plus 6. I need to get rid of my y coefficient, so I'm going to divide everything by 3. And I get y is equal to 2/3 x plus 2. So coming over to my graph now, slide this away. I'm going to graph my y-intercept of 2 onto my y-axis, and then use my slope of 2 over 3, so rise of 2 and run of 3, to give myself a couple more points on my line. Now when I'm solving with graphing, I give myself a lot of points. Okay, having as accurate of a straight line as you can, and I can't use a straight edge up here, but I would recommend that you guys do, because that point of intersection, you want to be as close to perfect as you can possibly get. All right, equation number 2, I'm going to switch colors here. So for my second equation, I want to, again, get it into y equals mx plus b. So I'm going to leave my y term alone for now, but I'm going to move that x term to the right-hand side. Yeah. Let me redo that. It'd be a negative 4x on the right. Leave the negative 9 where it was, and divide away the negative 6. So y equals 2/3 x plus 3/2. All right, so when I do that, notice, I think you would notice, that they do in fact have the same slope. So these are going to be parallel lines. They're not coinciding because they do have different y-intercepts. So with them not starting on the same intercept, they aren't coinciding, they're not identical, but they are going to run parallel to each other. So let me go ahead and graph the second one. Okay, so an intercept of 3/2 is going to be just below the other line, but they do not end up overlapping. Okay, so they're going to be ever so close, but yet parallel. Since they are parallel, they will have no lines of intersection, no solutions. All right. Checkpoint number 6, I think, no, this is number 42 off of our assignment. So if you guys want to take a look, or number 42 off of page 443, I decided I was going to go through an application or a word problem with you guys just to give you an idea of how to take the hints and the information from a story problem and create a system that you can use your favorite method of solving on. So, like I said, this is number 42 out of our exercise page. It says 2 planes start from LA International Airport and fly in opposite directions. The second plane starts a half hour after the first, but its speed is 80 kilometers per hour faster. Find the airspeed of each plane when 2 hours after the first plane departs, the planes are 3,200 kilometers apart. Okay, so we have 2 planes. We have different speeds. Okay, and we have some distance that we're going to cover. All right, so there are a couple of things that we don't know. We don't know how fast either of them are going. So we have 2 variables. Let's let x be the speed of the first plane. And then I'm just going to let a y be the speed of the second plane. Now they do give us a little bit of a hint as to the speeds. It does say, it says the second plane starts a half hour after the first, but its speed is 80 kilometers faster. So let's create an equation with that information. We've got speeds of x and y, but that second plane is 80 kilometers faster. So how could we create an equation? Well, take the first guy and give him 80 kilometers per hour more, and it should set his speed the same as the second guy. Okay, does everybody see where I came up with that equation? Okay, now one thing I am going to do right now before I continue on and come up with another equation, generally when we're solving systems we like to have our variables together on one side of our equation. So I'm going to take this one that we just created and I'm going to move the y to the left. So it's now a negative y, and I'm going to move my 80 to the right. So hopefully everybody follows me and sees that that's the same thing that I started with. But now I have my x and my y together. All right, now what else do we know? We know that it says find the airspeed of each plane when 2 hours after the first plane departs, the planes are 3,200 kilometers apart. So we know that the first plane went for 2 hours, and we know that the second plane took off a half hour after that. All right, so we technically know how long the second plane was flying as well. So the first plane flew for 2 hours, but the second plane flew for only an hour and a half. Okay, it was a half hour after that that one took off. So how is it that you determine distance? Well, it's speed times time. Okay, so if we have the distance of our first plane that we want, we'd have to take the fact that it flew for 2 hours and it had a speed of X kilometers per hour. Okay, how about the distance of the second guy? Okay, that one's speed was Y, and it only traveled for an hour and a half. Okay, so you can either use 1.5 or you can use 3 halves. I'm going to go ahead and use 3 halves. I like fractions better. So that's how far that guy's going to get. Flew for an hour and a half at a speed of Y. Okay, now both of those distances together, it tells us, get those planes to the point where they're 3,200 miles apart. So I can create another equation using these informations. So we have a distance of 2x added to a distance of 3 halves y, and those two together get those planes 3,200 kilometers apart. All right, now we can use our whatever method we like the best. Some of you, if you're a substitution method fan, that first equation in here has a plane x. So if you wanted to use substitution, you could go ahead and do that. I'm not the biggest fan of substitution, so I'm not going to use that one. I'm actually going to use elimination. So I'm going to go after the x terms by multiplying a -2 through my top equation. All right, so if I multiply everything there by a -2, I'm going to get a -2x plus a 2y equals a positive 160. Okay, so combined, my x's are going to eliminate. 3 halves plus 2. Okay, now 2 is the same thing as 4 halves. So 3 halves and 4 halves makes 7 halves. And then I'm going to get 3,360 on the right-hand side. Now, to get rid of my fraction coefficient, I just multiply by its reciprocal. So y is going to be equal to, and this is going to actually cancel. I can divide both of these by 7. 480, I think. So 480 times 2, I get 960. Okay, so y is the speed of my second plane. So that one was going 960 kilometers per hour. I need to find how fast the first one was. So I'm going to use that first equation up there. If we have x minus y, x minus 960 would equal -80. X is going to be 880 kilometers per hour. All right, so those are the two speeds of our two planes. All right, your assignments pages are 442 to 445. Please do lots of them. Get very comfortable with these problems, both graphing, elimination. Go back and work some more substitution ones from section number 1. You guys have had some experience with systems, so more practice just makes you more comfortable and the scores go up. That's all I've got for you.